Hi, in this video we're going to show how to use the transfer learning technique in the deep learning toolbox of MATLAB. In this technique we use a pre-trained network to classify new images by slightly modifying it. As this image shows, a pre-trained network can have millions of images and classify thousands of different objects, and we can modify the backend layers to classify, let's say, tens of new categories which was not trained for, and we could train it only with hundreds of images rather than millions of images. In this type of network, the input of the network is going to be the images, and the output is going to be the categories. So the closer the layers are from the input, the more related to the input they are, and the more general the features that the layers are going to detect. The closer to the output, the layers are going to detect features closer, more related to the classification categories. So the backend layers are more specific to classification, and the input layers are more generic. So we want to keep the front end layers and modify the backend layers to detect new categories. Okay, so we're gonna do this example first with the deepNetworkDesigner app, which is the graphic user interface of the deep learning toolbox, and then we're gonna use the command line API from the deep learning toolbox. Okay, so let's open the first example. Okay, we open the live script, and first we're gonna unzip the data. This folder has 5 different categories: a cap, a cube, playing card, screwdriver, and torch, and each of them has about 11 samples. So we have a total of 55 samples only to train this neural network, and we're going to show how effective this is with the small amount of data. Okay, so let's use the deep network designer, and the first thing is that we're going to load the SqueezeNet. Okay, and here we can see the different options that we have: SqueezeNet, GoogleNet. We can show more here. We have sequence to label. We can also create a blank new network or use from the workspace. We have saved it in a map file in a workspace variable. Let's choose SqueezeNet. Okay, so it's pretty big. We're gonna have a bunch of convolution layers, pooling layers, max pooling, some regularization, ReLU layers, some branching, and but we want to keep most of this almost every layer, because they are generally trained for detecting objects. So we want to only modify the ones that determine the output categories. So this is not the one that determines it. This doesn't. So this should be the one, because this determines the output categories. So okay, so we're gonna replace that. We're gonna replace that with another convolution 2D layer. We're gonna pick it from here. Okay, but we want it to be that the output is, well, we can see in here that the output is 1000 categories. That's what the SqueezeNet was trained for, but we want it to be trained for only 5 categories, because that's what the data has. And also we want the output to be a scalar. I mean the filter, sorry, this is the filter size, the weights filter size of the convolution layer. And also we want this layer, since this is the one that is going to determine the new categories, we want to train faster than the other layers, because we want the other layers to remain as they are, and for that we're going to change the learning rate later. Okay, so we just have to eliminate this. Okay, and finally this was trained already for 1000 categories, so we have to get rid of it so that it can be retrained again. We don't want its weights. Okay, so those are the two layers. So now we have the layers ready. So in order to have a neural network trained and used, we need to provide data, to provide the layers and training options. We already provide the layers. Now let's go for the data. We're going to import the image data. In this case, it's from the folder that we just unzipped. We could also provide it from an image data store in the workspace if we want more control. So let's just choose the folder. And also we can provide data augmentation, and this is useful if we want the data to be robust for affine transformations like rotations, translation, which for image detection is always the case. So that's the data augmentation is very common for this type of problems. And also if you have an image rotated, then instead of having one sample you have two, so you can have even more data. And that's especially important when you go from epoch to epoch, because in the second epoch, third epoch, you're gonna see different rotations of these affine transformations, so it's gonna make the neural network stronger. So let's choose flipping of the image horizontally. Let's do some rotation from 90 degrees to 90. We're gonna scale vertically, have the default for validation data, 30% of the data. And now let's import it and take a look at some of the samples. Here are some of the samples of the categories, and we have 11 samples for each of the 5 categories. Okay, so we have the data, so now we only need the training options before we start training the network. Okay, so we want to train faster the new layers. That's why we increase the the training rate for the weights and biases. But we want the rest of the network to remain as it is, because those are generally trained. So let's reduce the initial learning rate. We have 11 samples per folder, so let's choose that as the batch size. Since we are just training those 2 layers, we don't need that many epochs. And let's for each 5 iterations, let's use the validation data. We're going to use the stochastic gradient descent with momentum, and the momentum is going to be 0.9. And yeah, that's all we need. And also for each epoch, in each epoch you basically run through all the data, and there's going to be a different rotation, etc. for each one of them, as mentioned before. And also the order of the images are changed by this parameter. Okay, so now we have the training options, so we can just train the neural network. Okay, okay, so it's gonna use the validation data pretty frequent, and yeah, it was pretty fast, 95% accuracy. Validation, the validation is a little bit below the training accuracy, so it means that maybe it might need some improvement in regularization, but it's pretty fine. But 95% is pretty fine. So now we want to try the trained neural network, so we're gonna export it as an object into a base workspace. Okay, so let's try it out. Okay, so this is our trained neural network, so we're gonna use it. Okay, so let's just read the image that is used for testing, this image here. Let's load it. Let's reshape it so that it can fit the input of the neural network, and then we're gonna get the corresponding output. This is the function that the documentation is using, but it should be done like this, because classify is a method of the neural network class. So the input is gonna be the image, and the output is gonna be the label and the probability of all the 5 categories. So let's try it out. So it's a cube, and the cube is the second category, so it has like 99.9, basically it's 100% of confidence that is a cube. Okay, so now let's generate code for this. Okay, so this is gonna generate a couple of artifacts. One of them is the script, and the other is a math file, and the math file is gonna have the properties. Sometimes it could, if in this case the data is provided from a folder, so we're gonna just create a data store using the folder path with the configuration of the label source as folder names, and then split using this deep learning command of splitting the image 70% for training and 30% for validation. But if instead of providing a folder we provided a data store, then it will have been part of this map file here. Okay, but that in that case, in our case, that map file is going to provide the properties for the neural network, like biases, probably, yeah, it's mostly biases, the mean for the input layer, for normalization. Yeah, so that's what this object is carrying, at least for this example. Okay, so the data augmentation of affine transformation, rotation, rescaling is done in this augmenter. We create an augmented data store with the input resizing of the input images that applies for validation and training, but validation does not have the affine transformations, doesn't need them. And then the options, the same ones that we chose for 8 epochs, batch size of 11. Data augmentation is provided in here. The graph is the SqueezeNet that we used, and you can see at the end in here, this is the convolution layer that we created with 5 categories and the final layer. Okay, so all the layers are connected, and I suppose that this should be for the branching, because the sequential branching should be done automatically. Hopefully there's no waste in there. And finally, you pass the data stores, the network, and the options, call the train network command, and we get the train network in here. Okay, so that's for the generated code. Now let's try this example with the Deep Learning Toolbox command line API. Okay, now we're gonna do exactly the same example, but with the command line. We're gonna create we're gonna unzip the data because it's another folder, and we're gonna use an image data store from the provided folder, and using the subfolders as the labels, and we're gonna use the same split command to get 70% of training data, 30% of validation. Okay, let's take a look at the data store. Here's our data, around 70 images. Okay, and these are the labels. Cap, yeah, should be 5 of them. Okay, so we can use different neural networks. Let's use GoogleNet, and we can use the analyze network so that we can, if you, well, let's use it. Okay, so we have here the input is 224 by 224 by 3, and the size of the image gets decreased all the way until it's scalar, and the number of features augments all the way until you have the 1,000 categories. So these are the layers that we want to change. The GoogleNet has some branching, a bunch of branching. So we're going to change this. Because this is classifying 1,000 categories and we only want 5. Okay, so we need the input size of the first layer, which is the input layer, as we already saw. And now we're gonna get the graph object, and in this case we are not a series network, so we use this command. And now we're gonna find the layers to replace using this command. I'm not. This is actually this function from the example, but I'm not gonna go through it. As you can see, this found this loss tree classifier and the output classifier, but it's a little bit more complicated than it has to. You can get the same layers directly. This is the one of the layers. This is the classified layer, the same one. and this one is the loss classifier. You can search it by name also. You see it's the same one. You have to go so complicated. I guess it is a little bit complicated in this example because this example is ready to handle a bunch of type of layers, so that's why I'm not going into that. Okay, okay, so these are the 5 labels from the data store. This is for all the input data. 55, we have 55 samples. Okay, so yeah, the number of elements of categories is 5, and that's what we're gonna have in here. Because now that we have the layers to replace, we want them that the learnable layer is, instead of being 1000, or as you can see right now, the output size is 1000. We want the output to be size of 5. So let's see which one applies to us. So this layer is a fully connected layer, so that's the one that we're going to create, a fully connected layer. Yeah, that's the layer that we're going to replace. So it's going to have 10 categories. No, sorry, my bad. It's going to have 5 categories. 5. This is the weights, the learning rate for the weights. So it's going to learn 10 times faster than the other layers for weights and bias. And this is going to be a new name. Okay, so we have the new layer. And now we're going to replace it using the name of the old one, which is loss classifier tree, provide the new layer and the graph, and this new deep learning method, and we just update the graph like that, replacing the layer. Okay, so now we can create just a plain classification layer, because since the old one was trained, let me show the old one. The old one has 1000, we have to change that. So we're gonna provide the new one and replace it by name again. Okay, the graph is updated. Let's take a look. We can see in here that this is the 2 new layers. Okay, but that's not it. We want to that these layers, especially this one, be trained faster than the other layers, because the other layers are generic and we don't want to change them much. So as mentioned before, the front end layers are the more generic ones, and we will not like to change the weights for those one. That's why we're going to use this deep learning toolbox command called freeze weights, which is going to set the learning rate to 0 of the layers given. So we're going to pick up the layers from the graph and the connections, and the first 10 layers we're going to freeze them. And since since we change a couple of layers and freeze the front end layers, we had to connect them again. So we use this method from the example that is just gonna create a new graph, adding all the layers, provide on the connections and reapply the connections. So it's like, I see this as a little waste, but I guess has to be done. Okay, now we have our neural network layers ready. We need to provide the data. We already loaded the data in here with the image data store from the folder, but we need to provide data augmentation, the affine transformations that we did before, rotation, scaling. In this case, we're going to provide scale and translation and horizontal reflection. Again, providing that only to the training data. And we have to resize using the size of the input of the neural network. Okay. So we have the training data, and the validation just needs reshape only. So again. Okay, so now we have the data ready, the data store, so we need only the training options. And for the training option, we provide the validation data. The learning rate is going to be low. We only use 6 epochs. Stochastic gradient descent. Validation frequency is going to be, we're going to use the number of files, which I think it should be 55. Whoops, number of elements. Yeah, 55. And you divide it by the batch size, which is 11. No, 10. So yeah, so basically the number of iterations in an epoch is basically this same formula. So what this is saying is that a validation is going to be used at the end of each epoch. Okay, so let's get the training options, and now we have the training options, we have the graph, and we have the data stores for the training data. So we just use train network to get the train neural network. Okay, so we have only 55 images, so this should go pretty fast. And let's see how we only have 6 epochs, and you can see that the validation is done at the end of each epoch as expected. And yeah, maybe we might need some regularization, but to improve this is only 90%. The SqueezeNet that we used before, doing something very similar, gave us like 95%. So yeah, we, at least for this example, the other pre-trained neural network did a little bit better. So let's close this. Okay, now let's try it out. Notice that the classify method, when you from the neural network class, takes an image and gives you the label, the corresponding label of the category. But if we provide a whole data store, then it's going to apply the classify method for all the data in the data store. We have 20 observations, so we're going to have 20 observations in here, and this is going to be for each sample, we're going to get the probabilities of all the 5 categories. Okay, so let's take a look. You can see that these are 20 samples and the probabilities of each of the 5 categories for each of the samples. And for example, in this one has 100% certainty that is the first category. In this one. So also we have the labels for the validation data, so we can compare them against the predicted labels here, which you can see that they are almost the same. So if we compare them, almost all of them are matching, some of them are not. So let's just take the average to compute the accuracy, 90%, which is the same that we got from the training network command report. Okay, so now let's pick randomly 4 files and just display, using the index, display the predicted label for that particular image, and display the image along with it, just to see it graphically. Okay, so in here it predicted a torch, but the torch is almost hidden, so that's why it has low confidence. In here the torch is pretty visible, 100% confidence. So screwdriver, very visible. Yeah, so so we showed how easy it was to take a pre-trained neural network, modify the backend layers to provide new categories, and with few images we were able to quickly train this neural network to be able to detect new categories. So I hope this is useful. Thank you for watching.